Okay, so now we're going to look at how light moves through different optical devices like mirrors and lenses. For mirrors and lenses, we're going to define some various distances, and the first of those is going to be the object distance. And for lenses and mirrors, then the object distance. This is the distance from the mirror or lens, whichever it is that you're using, to the, wait for it, the object. All right, so it's fairly obvious just how it's written. And then also the image distance, as you might expect, is the distance from the mirror or lens to the image. You can see a variety of variables for these. So object distance, I'm going to call P, and that's fairly common, and it's the distance to the object. So object distance, I'll call P. This is the distance to the object. Sometimes you'll also see it called DO, the distance to the object. And then the image distance is usually called Q, but this is sometimes called DI. But I'm going to call them both P and Q. And then we have a few standards about what signs for these various things mean. If Q is positive, the image is a real image. And real images are defined because they can, in such a way, they can be projected onto a screen. If you're in the lab, you've seen both virtual and real images. But for example, in your bathroom mirror, that would be a virtual image. You cannot project your bathroom mirror image onto a screen. However, you can produce some real images with mirrors, and we can see that in various things. But more commonly, you'll see real images like with a projector, with lenses and what have you. Now, if Q is negative, the image is a virtual image. And while you can see the image, you cannot project it onto a screen. Like in your bathroom mirror, for example. All right, so if Q is greater than 0, it's a real image. If Q is less than 0, it is what we call a virtual image. Real images can be projected onto a screen. Virtual images cannot be projected onto a screen. All right. Now let's look at flat mirrors. This is sort of the most common type of mirror that you know. For flat mirrors, the following is true, and that is that Q is equal to the negative of P. So what kind of image does a flat mirror produce? Well, P is always positive for a flat mirror. That's your object distance. So that means that Q is negative. It has a negative Q, and that means that it is a virtual image. We'll play this clip in just a minute, but let me, actually no, we'll go ahead and do it right now. This is a clip, Richard Feynman, he's a famous physicist, won the Nobel Prize. He's kind of quirky too, so people, I don't think people now these days really listen to him that much. I think he's even dead. But used to, he was fairly popular. He wrote a couple popular books, and just kind of a quirky guy. So here he's talking about flat mirrors and how the images appear to us, and how the images appear differently from the actual object. So let's just watch this. This is really just sort of for your own interest, but it's kind of funny. All right here. All right, now let's define some things about magnification. We're going to define magnification in two ways. And in the first way, we will compare the height of the image to the height of the object. And so our magnification is going to be image height divided by object height. All right, a magnification of 1, if our magnification equals 1, that means that the image is the same size as the object. Like in our flat mirrors, we have a magnification of 1. That means that we are the same size as we are in real life. A magnification greater than 1 means that the image is larger than the object. and a magnification whose magnitude is less than 1. So I'm going to say that my magnification is less than 1. That means that it is between -1. My magnification is greater than -1 and less than 1, somewhere between 1 and -1. And that means that the image is smaller than the object. You'll see why they have this distinction here, because a magnification of, say, -2 is not smaller than the object, even though that magnification is less than 1. All right, and if the magnification is negative, then that means that the image is inverted, it's upside down. And the image height, we call this Q, is also negative. Okay, I'm going to summarize all these in a table in a little while, but these are all just sort of standards that we adopt for describing images and mirrors and lenses. Actually, it looks like I'm going to define it here on the next page. All right. Now, if the magnification is positive, then the image is upright. And in this case, the image height, which we call P, is also positive. All right, so upright images have a positive magnification. Inverted images have a negative magnification. All right. I'm sorry, I did something wrong here. Let me fix this. The image height is not P. That would be the image distance. The image height is HI. And then on the previous one, I had another mistake. So if you'll fix this, the image height is not Q, it's HI. Okay. Here's a little table. If our magnification is bigger than 1, my image is bigger than the object. If it's less than 1, and actually I'm going to say if it's less than 1 but greater than -1, the image is smaller. If it's the same size, it's equal to 1. If the magnification is positive, the image is upright. If it's negative, the image is inverted. I think that's a good place to stop.